أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture of the course of Thermodynamics, having the course code of PHY331, I will discuss something about heat and first law of thermodynamics. This is the third chapter of our course. From this lecture we have some objective, and these objectives are the understanding and reviewing the concept of heat and work. We need to know the concept of adiabatic work, and at the end of this lecture we will discuss about internal energy function. The first thing is work and heat. The old concept about work and heat, and the understanding of work and heat. The first thing is that how we can change the state of the system. Actually, in the whole chapter, in the whole last chapter, we discussed about work, and work was actually used to change the state of the systems, and state of the system is actually changing the value of the thermodynamic coordinates of that particular systems. So how we can change the state of any particular system? We can change it by bringing the system from initial to final state, and we can calculate the magnitude or the amount of work done. How we can do it? If we do the work, we have two systems over here. This is the first systems, in which there is a pulley in a cylinder. The whole system is closed in adiabatic surrounding. I mean, no heat can enter or no heat can leave the systems. So there is a pulley or a fan inside the water, and that is connected through a pulley with the load. As the load go downward, the pulley is moving or the fan is moving, and that will heat up the water. In the other figures we can see there is a resistor, is a type of electrical systems, and this resistor is connected with the with some sort with a pulley, and over there is a weight connected to a pulley, and that is moving a pedal through it, and as a result of moving these things, some induced EMF will be created, that is used by the resistor, and it will heat up the water. So in both cases work is done, I mean the water temperature increases. So we have this the first one is a simple system, and this is a composite system, that is the combination of electrical and mechanical systems. So how work is done in this particular system, this is one example. The other is about heat, how we can heat up any particular systems. So we can change the state of any particular system by other means as well. The first thing what we discussed was to change the state of the systems by means of work, and changing the state of the system is nothing but it is actually changing the value of the thermodynamic coordinates. That is possible by means of work or heat. In the first figure we are observing a kettle of water or a cylinder of water that is placed on flame. So the flame is heating, and as a result of this heating, this is actually a heat source. The water is absorbing heat, so it means a type of heat is coming from the heat source or from the flame toward the water. So this is also, we can change the temperature of this system, and we all know that temperature is a state variable, and that is why the equilibrium configuration of the system will be disturbed. The other is that in the other figure, that is actually the fourth figure of this slide, there is a open cylinder, there is a open pot of water, and it is placed in an adiabatic room near a heating source. So as a result of this heating, as its temperature is higher than the temperature of water, and both are in thermal contact, I mean because of air is in thermal contact with each other, it will create heat, and this heat will be absorbed by water. When water absorbs the heat, its temperature will increases, and as a result the state of the system will change. So from this slide we understood that we can change the state of a system with the help of work and heat. Work is used to change the state variable by means of doing some work, and heat is also used to change the state of a system by changing the thermodynamic variables. So we can place two systems. When we place two systems in contact with each other that have different temperatures, so what happen, actually this is the zeroth law of thermodynamics. When two systems are placed in thermal contact with each other and both the bodies have different temperature, so what happen, the heat will flow from a body having higher temperature towards a body having lower temperature. So what is the concept about heat? In 19th century it was believed that heat is nothing but it is a liquid, and that liquid was given a name of caloric. In some book is given as the name of caloric, and in some places is called as a ether. But anyhow, that was assumed to be an elastic fluid that is present in every body. So a body that has high temperature has high magnitude of that particular liquid, and a body that has lower temperature has low magnitude of this particular calorie. So bringing the bodies in contact with each other allow the calorie to flow from a body of high temperature towards a body of lower temperature, and this motion of calorie or this movement of calorie continues until both the body achieve the same temperature. So this was something, an idea about the heat in the beginning of 19th century. So now the heat concept is changed, and heat is considered to be energy, and we will discuss it in next lecture as well, how heat is considered to be an energy, and that is why heat is measured in the unit of energy, that is joule. So heat is that which is transfer, when normally it's called as heat is that which is transfer between a system and surrounding by virtue of temperature difference only. When there is temperature difference between two bodies, so heat will be transferred from a body of higher temperature toward a body of lower temperature. So we have different systems we need to understand in this lecture. That is the adiabatic wall. Adiabatic walls are called as a heat insulating walls, in which heat cannot be passed. We have diathermic wall as well, which allow the heat for movement on both sides, and that is called as a diathermic walls, which is a type of heat conductor, and adiabatic is a type of heat insulator. We need to know the system, that is the thing that is under observation is called as a system, and surrounding anything anything that is not included in the system is called as the surrounding. So we need to know what is adiabatic work and how we can calculate the adiabatic work. First we need to consider a closed system that is surrounded by completely adiabatic boundary. So we need to know how the work is done in this cases when it is completely surrounded by adiabatic boundary. So we need to state the state of the system. We need to move the state of the system from an initial state to some final state, and this change can be performed with the help of adiabatic work. So mechanical systems are not easily controlled in changing the state of a system. So this is something about a combination of a composite systems in which there is some mechanical system and there is some electrical system as well. There is a weight that is connected through some pulley with some some ropes, and that when the weight is moving down, it is allowing the pulleys to move, and maybe they can change they can induce some current, induced EMF, and this current is used, or this voltage induced EMF is used to run a resistor that is immersed in water, and that will heat up that water and to change its temperatures. So this is actually a composite systems in which a resistor, that is the electrical system, is immersed in water. So we need to change the state of a system from an initial state, that is actually V, in which the pressure PI is equal to 1 atm, temperature is equal to 287.7 K, and similarly the final configuration of the system is that the pressure is the same, but only the temperature is changed by single degree. So its temperature is equal to 288.7 K. So how we can proceed the system from an initial to final state, we need to know in the adiabatic work. We have another system that is comparatively simple, in which a gas is enclosed in a cylinder. There is a piston above the cylinder, but that piston is movable. When some force is applied on the piston will move downward. When there is no force on it, it will move upward. So we can do some work by these systems. What we do, we place some weight on this piston. So as a result of this weight, the system configuration is changed from an initial state to final state, and system will do some work. So this is actually, in this case, the boundary what we are considering is are adiabatic, are insulating. I mean, no heat can leave or enter the system. So this is an example of adiabatic work as well. So I mean, initially, if the piston is present over here, so what happened when we place weight on the pistons? So the piston move downward, and as a result, it covers some distance dx. The force is applied. The force is actually, in this case, the weight. So the force multiplied by the displacement is the work done, and in this case it is called as adiabatic work, because both the piston and the walls of the cylinder are adiabatic. I mean, no heat can enter or leave the system, but we have changed the configuration or the state of the system from an initial to final state with the help of adiabatic work. We can describe the state of this particular system or moving this system from an initial to final state with the help of PV diagram or with the help of PV curve, and that can be easily, we have actually three paths to move from an initial state I to a final state F of that particular systems. So the first path is only adiabatic work can proceed, and this is very easy path. This is actually the shortest, I to F. This is actually the first path of this system, and in this case adiabatic work can proceed the system from initial to final state and surround the water with adiabatic wall, keep the water at atmospheric pressure, and maintain the current in the resistor from suitable interval of time. When we maintain the current, the water temperature will change from initial to final state, and it will change by a single degree. The other is the second path. The second path goes through this way. I mean, this path is going from I to F. This is the second path of bringing the system from an initial state I to a final state F. So we need to compress the water adiabatically from I to A. At first case, what we need to do, we need to compress the water from I to A. This is I to A, and use the current in the resistor from A to B. In this case, we can use the current to heat up the water, and what happen, the water will expand from B to F. This is the second step. So this is the second part to move the system from I to F, and in the same way we have a third path that is similar to the path second, but is a bit different from it, because we need to perform the pressure and to reverse the nature of process and bring the system from an initial to final state to this path. So there are infinite number of ways or infinite number of paths by which we can bring a system from an initial to final state. Here we have only described the three ways, but there are actually infinite number of ways to bring a system from an initial I state to a final state F. So if we generalize the concept about bringing the system from an initial to final state, what will happen? The generalization will show that the adiabatic work along different paths between two same points is always same. And this generalization is a restricted statement of the first law of thermodynamics, which says that any closed system that is caused to change from initial to final state with the help of adiabatic process, then the work done in the system is same for adiabatic path connecting the two systems. So it means if we are moving in all these paths, the work done is in case of adiabatic, and if there is no friction, if we assume or we neglect the frictional force or other some resistive forces, then we can consider that the work done is same through adiabatic work done is same through all paths. So when any quantity depends only on the initial and final path irrespective of the path followed, then we need to develop a very important conclusion about these ideas. If we consider in mechanics, when we move an object from one point to another point in the gravitational field and ignore the frictional force, what happens? The work depends on the 2 points and not on the path followed. This is something what we have learned in mechanics, but this is really ideal situation because we are ignoring the frictional force. Here in this case as well, we are also ignoring the frictional or other some dissipative or resistive forces which can dissipate the energy. In conservative force, when there is a conservative force, there exists a function of space coordinate of the body whose final value minus its initial value is equal to the work done, and this function is called as potential energy function. So the work done in moving an electrical charge from one point to another point is also independent of path. If we can move a system from initial point, one point to another point, that is also independent of the path, and the value of that electric potential function is equal to its final minus initial states. That is very simple. So if we consider the restricted first law of thermodynamics, so there exists a function of the coordinate of the thermodynamic whose system whose value at the first state minus its value at the second state is equal to the adiabatic work done. I mean, we can get its value or the value of the work done of the system from an initial to final state of that particular systems. So this function is known as a internal energy function, and the internal energy is represented by symbol U. So the work done is equal to bringing the system from initial to final state. Keep in mind we are considering the work to be an adiabatic work. I mean, no hard enter or leave the system, which is a type of ideal situation. So in this case, for positive work we can consider UF is greater than UI. So how we can discuss the internal energy function and what is the physical interpretation of this internal energy function? If UF is greater than UI, that is the final internal energy is greater than the initial internal energy, so it means that the system internal energy has been increased, and actually this equation shows the difference of internal energy that is equal to the work done. So this equation basically describes three states. This equation basically describes that there exists an energy function whose difference between two values is the energy of that particular systems. So internal energy is a function of as many thermodynamic coordinates as necessary to specify the system. Say for example, if you are considering a hydrostatic system, so in which there are three thermodynamic coordinates, so internal energy of the will be a function of that three thermodynamic coordinate, but anyhow it will be a function of two thermodynamic coordinate, because in that case we have two independent thermodynamic coordinate and one as a dependent thermodynamic coordinate. So in thermodynamic system, just we have discussed among the three thermodynamic coordinate, we have two as an independent thermodynamic coordinate and one as a dependent thermodynamic coordinate. So internal energy is a function of two thermodynamic coordinate. So if we want to calculate the magnitude of infinitesimal change, so how we can do it? We can also calculate it from the value of du that describe the infinitesimal change in the internal energy, as we have considered that for any hydrostatic systems there are two independent thermodynamic coordinate and one is dependent. So the value of dependent thermodynamic coordinate could be calculated from the equation of state. In this case, when we consider tv as a independent thermodynamic coordinate, then du will be a function of t and u. We can write this equation in this way, that change in internal energy with respect to t at constant volume into dt plus change in internal energy with respect to v at constant temperature and change in dv, that is its values. So similarly, when internal energy is a function of u, so what happen in this case? Internal energy, the internal energy is a function of t and p, so it means temperature and pressures are independent variable and the volume is dependent variable in this case. So we can calculate the magnitude of change, that is will be the change in internal energy, that will be equal to du, that is top, is equal to change in u with respect to t when pressure is constant plus change in u with respect to p when temperature is constant. So this is something about the work, heat and internal energy. I hope we can develop the mathematical form of first law of thermodynamics and some relevant ideas about the first law of thermodynamics in the upcoming lectures. Thank you very much.